Okay. And I realize now that I don't really have all. Okay, now we're going to take what we learned about these two-state paramagnets and apply them and treat them as an actual system that we can measure things out of: temperature, energy, magnetism, things like this. So let me draw up on the board again what the situation looks like. Say we've got a magnetic field which is capital B, which is directed upwards. And our individual paramagnets are going to be little, we call them dipoles. Actually, I say paramagnets. Our little dipoles, there we go, are, they can be aligned or anti-aligned. And so on like that. Now, one really key thing to remember. When one of these dipoles, one of these arrows, when it's lined up with the magnetic field, that's the low energy state. That's the way it wants to be. Hamilton's principle, not actually named for me. Nature is lazy. I don't want that one attached to my name. Nature takes an easy way out. The lowest energy state is when it is, or nature seeks out the lowest energy state. When the dipole is aligned with the magnetic field, it's in the low energy state. Unfortunately, we universally draw these things with the magnetic field pointing up, which means pointing up is the low energy state. Pointing down is the high energy state. Okay. So, let's see here. I'll draw an energy level diagram. It has each of these has one of two energies. It can either have an energy of, and I believe we found this energy or asserted it in in chapter 2 when we first introduced these, plus mu plus mu b, where mu is called the dipole moment. Moment, like there's moment of inertia, well, there's a dipole moment as well. And it's simply a number that is associated with the strength of this little dipole's magnetic field. Where B, then, is the strength of this external magnetic field they're trying to align with. Okay, a dipole can either be in the high energy state, which is, so it's either this state up here, and those are the ones pointing down, or it can be in the low energy state, which has an energy of negative mu B, exactly the opposite of the high energy state. Okay? And that's if the dipole is pointing up. Again, a little confusing that we have the magnetic field going upwards. So anyway, the down state is the high energy, the up state is the low energy. If you can get that straight, the rest follows easily. Remember, up is pointing with the magnetic field. That's the key thing. All right. Now, let's see here what we're going to do. All right, I want to write out the total energy of the entire system, a collection of all N, capital N, dipoles. Okay, the total energy is U. Well, let's see here. Let's say we have capital N of these dipoles. Some number of them are pointing up and have this energy, negative UV, and some number of them are pointing down and have this energy, positive UV. So the total energy is the number pointing up, let's start with the hydrogens. So it's the energy of the high energy state times the number in that state, in down, plus the energy of the low energy state times the number in the low energy state, in up. Clear enough? Okay. So this is simply adding them all up. All right, we've got this many in the down state times the energy of the down state plus this many in the up state times the energy of the up state. And we can simplify this. We can factor out a mu b and so now we have mu b times the number down minus the number up. Okay, at this point it's a little bit awkward if we keep trying to put it in terms of number down and number up, because what we've really got access to is the total number of these. So we could put it in terms of the total number and say the number down. Those are the ones in the high energy state, so they're more interesting, maybe. Either way. Okay, so let's rewrite this in terms of in and in down instead of in down and in up. Okay, so if the total number in is the number down plus the number up, then I want to get rid of the number up here. Then number up, I solve for that, that's in minus in down. All right, I just plug that in for number up. Okay, so minus in up is minus, parentheses, in minus in down, so that's minus in plus in down. Okay, simplifying, I've got in down minus in plus in down. We can see that that is in minus 2 in down. Oh wait, did I put that wrong? Hold on. Aha! I did write that wrong. Let me see here. I've got an error on one of these. I want to write it in terms of the number up. It's how, at least how I did it here, and honestly how the author does it in the book.
He has the n total minus 2n up.
Yeah. Okay. So I should solve this instead for the number down. And I can get rid of the number down. Okay. Now, I use that in here. So I've got in minus in up minus, hold on a second. Yeah, okay, that's right. Good. Fine. Now I've got n minus 2 times n up. Okay, so I've got an equation for the system's total energy in terms of mu b. Remember, mu is the magnetic field strength of each dipole, and b is the external, outside magnetic field strength that's they're trying to line up with. And now total number, which is we'll take to be fixed, minus 2 times the number pointing with the magnetic field. Okay, so far. Well, let's. There are 2 more things I can do with this that it turns out is going to be useful here. One more thing I can do with this. This is good on itself. This is a formula for the energy. But let me show you. Let's solve for, let's see here. if I divide both sides by negative b, so negative u over b equals, well, let's see, once I take care of the minus signs going through, I come up with mu times 2n up minus n. And you might wonder to yourself, why do I care about this form here? Well, it's because I've already done the derivation for the rest of this, and it turns out we're going to use this later. It's not an important equation on its own, but it'll be useful later. This that I've boxed in is important on its own. Okay, so we have an equation for the energy in terms of magnetic field details and the number up. Next thing we want to measure. Now, a paramagnet, volume is not a big deal with it. So while we often talk about number, volume, and energy, here volume is not really an issue, but we do have another thing we can measure on it, which is the magnetization. Let's find out the magnetization. Okay, close it. We'll call that capital M for magnetization. Magnetization is defined as the total magnetic moment of the system. Now remember, the magnetic moment of a dipole is mu. Well, that's either plus mu, if it's up, or it is minus mu, if it is down. So, magnetic moment okay. Plus mu if it's up, minus mu if it's down. So, the magnetization is the total for the whole system. Capital M. So we add up. So we got negative mu times the number down, plus positive mu times the number up. Well, once again, now we simply added up the total of all of them. Let's put it in terms of the total number and the number up, just like before. Let's see, first we will factor out a mu here. So we've got mu times number up minus number down. And just as before, since the total, n, is the number up plus the number down, or I've got to see the number down plus the number up, then I want to get rid of number down. I solve for the number down here. There. Number down is number minus number up. I plug that in. And what I get is 2 times the number up minus the number, total number, all times mu. Which by itself is perfectly nice and interesting, but it turns out it's even more useful if I recall that previous little equation here at the bottom. 2n up minus n is, well, let's see, mu times 2n up minus n is negative energy over magnetic field strength. external field strength. So, like I said, I kind of peeked ahead. So let's rewrite the magnetization in terms of the energy and the total magnetic field strength. And we get negative U over B. Nice little result that the total magnetic moment of the whole system is going to be directly related to the system's energy. Okay. Great. What are we going to do with that then? So recall that we got a series of instructions from before. What we're often going to do with systems is from pages 92 to 93, a series of steps. First, figure out how the system works down at that probably quantum mechanical level, statistical level, and find the multiplicity as a function of whatever the interesting variables are. Often U, V, N, etc. In this case, we'll have M in there. We won't have a volume. Okay, so once you've found the formula for the multiplicity, then take the natural log times K, you'll have the entropy. Once you've got the entropy, take the derivative with respect to the energy, holding the other things constant, and you'll find the temperature. Holding all the other variables constant. Okay, this is going to get you temperature as a function of energy. Next, solve for energy as a function of temperature. And finally, find the heat capacity as from this here. So heat capacity at constant volume is the partial derivative of energy with respect to temperature, holding all the other things constant. Okay, let's try this here. Let's find the heat capacity, and you might wonder, why do we care about the heat capacity? Well, that's just sort of the final thing we can get. Temperature, to tell you the truth, is going to be the weird and fascinating thing about this here. And that's really where I'm wanting to get to today. See how far we can get with it. Let's see if I can easily zoom it out. Okay, that's good enough. All right, everybody ready? Kind of a race at this point, it feels like. We know the goal, we know where we're starting. Let's see what we can do. Step one. Well, step one is easy, we've already done it. Find the multiplicity as a function of other things. We just look up on page, equation 2.7. So the multiplicity as a function of the number of dipoles pointing up is n factorial over n up factorial, n down factorial. That's not all that helpful. We want it in terms of total n and n up only. So we just rewrite this, which we did before, equation 2.7. Well, we still got a factorial in there, and we don't like factorials. But step 2 is to solve for the entropy, which we get by taking the natural log. K natural log of omega. Okay. Let me divide both sides by K, because that way I don't have to keep keeping track of that factor of K on the right-hand side, which will have a whole lot of terms added together. So, S over K equals the natural log of this. So, natural log of n factorial minus log of n up factorial minus the log of n minus n up factorial. See, in fact, did we already do this, derive this out into, we took Stirling's approximation? I don't recall if we've done that yet. Well, we're going to do it now then. Okay, next thing we do, equation 2.16, Stirling's approximation. Where natural log of anything large, any very large number factorial, is actually a large number. Large number, not very large number. N log n minus n, approximately. Now, that doesn't only apply to n factorial, it applies to any large number factorial. Okay, so I'm just writing it down there. All right, let's do that for each one of these here. First term, n log n minus n. Second term, we have the minus sign overall, so I'll put it in parentheses. N up, log n up minus n up, all in parentheses. Third term, somewhat messy. We've got a minus sign overall, so we put it, and we've got the parentheses already in there, I'll put it in square brackets. Okay. N minus n up, log n minus n up, minus n minus n up. Okay. I'm going to distribute these minus signs. So n log n minus n, that doesn't change. Minus, now I'm going to distribute the minus sign here. N log n up plus, some minus sign here. Minus n log up, minus n up log n up plus n up. Okay. Minus parentheses n minus n up log n minus n up plus, let me break that last one out, so it'll be plus n minus n up. Now, this lets me simplify just a little bit. minus n plus n. Those cancel out. Plus n up, minus n up. Okay, I've gotten rid of 4 terms right there, which is nice. All right, rewriting what I've got left over. Okay. Now, let's see. At the same time, I'm going to try to think if this was actually useful or not. Yep, apparently so. Let me just see here. Yeah. I think I'll go on and distribute these. Let's see, the first term there. Okay, so I've got now minus n log n minus n up. Plus n up log n minus n up. Okay. There. That's the entropy of divided by K. Everybody feel happy and satisfied that you've got this there, and this has deep and great meaning to you, I'm sure. Let's see what we're going to do with it. The next thing to do, looking back on our list, once we have an equation for the entropy, we take the derivative with respect to energy, holding everything else constant, to find temperature as a function of energy. We're going to have to put this in terms of energy then, aren't we? All right, that'll be our next task. Yeah. Okay, let's see how well the board is visible. That isn't too much. Magnify. All right. Step 3. Water over temperature is ds by du. With everything else being held constant. In this case, what are the other things? Number and magnetic field are going to come into this.
Do you have an extra n in there on your third set after the minus? Keep going. Right there. No, right back. Go back. There. That n.
All right, let's see here.
Because if you pull it down directly from your thing, yeah, there's not an n. But you have that after. Right there. So you already have that, and you don't have the one in marked out.
What have I got wrong? I'm going to put the screen back on this.
Where are you putting your other? Right, if there's your n right there.
So let's see, n log n here, minus n up log n up, that's here, minus, and we have n minus n up, both times this. So minus n times that.
Oh, I see. Okay.
And then minus minus, that's plus n up times the same bit. Is that clear enough? Okay, good. Okay. So, to find the temperature requires entropy as a function of energy. Right now I've got entropy as a function of number of light bulbs pointed out. So, I've got to put it in terms of. Let's see. Actually, right now, this reminds me of something that you were looking at doing on the homework. Rather than trying to put in, it could be a mess. if I were to take that long equation that we just derived with an n up in almost every term there, and try to put in our equation for energy, which you can solve for in terms of the number of. Fine. But we're going to have an enormous number of terms. If you look back, we had U equals mu b times, parentheses, n minus 2n up. If I solve that for n up and substitute that into each one of these terms in entropy, U in there, I've got a whole lot of terms floating around. Not particularly difficult, but tedious. I don't like the tedious part. So instead, what we will do is change this using the chain rule from a derivative of s with respect to u into a derivative of s with respect to n up. And that'll give us another term, which is the derivative of u with respect to n up, or n up with respect to u, but that's okay, that's easier. I like the chain rule. The chain rule always seems like cheating. Okay. So ds by du is the same as ds by dn up times dn up by du. Holding the other variables constant. Remember, you can always, if you're not sure if you did it correctly, well, just cancel out whatever that is there, above and below, and you get back what you had to get there. Okay, so this means I can find dn up by du very simply. And then then the hard part is taking the derivative of s with respect to n up, which is not bad, it's just, a bit tedious. All right, let's see here. Let me get this one first. All right, so we're calling that u equals mu b times n minus 2n up. Then, let me solve that for n up. Let's see here. Oh, I know what. I can do it even, I could do this, in fact, just that way. Recall this from before, so from the first form. I could solve for n up, which will be then a function of u, and take the derivative, right? Or I could do this even more, which seems like cheating. A over b is 1 over b over a. Well, it applies to derivatives as well. A derivative is not merely some kind of symbol. It is a ratio, a small amount of n up divided by some small amount or small change in u. As long as I don't divide by 0, I'm okay. So this is, let's see, the first term stays the same. One over du by n up. As long as this doesn't turn out to be 0 somewhere, so I'm not dividing by 0, it's okay. The thing is that while in the mathematics books, this always seems like cheating, and they give you dire warnings about, well, this is only valid under certain conditions, and blah, 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 you're not dividing by 0. We don't generally come across those exceptions in physics. Most of nature is pretty well behaved, mathematically. There are places where it's not. We get singularities and black holes and things, but here we don't have a problem. Okay, that's easier to do. Now I don't have to solve that extra term. I just flip it upside down there. So, let's see here. First term is 0 minus well, that was easy. Let me turn this around so I have 1 over, minus 1 over 2 mu b, and then times this here. here's where all the work comes in. That's going to be a few lines, but I think we're up to it. It's going to be 1 over temperature. Trying to see if I've got enough chalkboard for this thing here. Yeah. I'm just not entirely sure if the camera's going to see it. Let me see if I can zoom in anymore. And this is where it's supposed to turn. So we will make it do it by hand. Okay, and we'll see just how well this thing captures the screen. What I really would like would be to have like 3 cameras, each one pointing straight onto a different section of board, and then I can just in post-production, cut and paste. Something. Okay, ds by dn up is what we need to find now. And then we're going to substitute that into that, and we'll find the temperature. That last step will be easy. It's this middle part of the stuff. Okay, ds by dn up. That shows. Now, if you go back to a couple of screens back, we had some ds by dn up. So that's going to be K, Boltzmann's constant, times a whole mess of stuff. I'm substituting in directly from our last line of the equation for entropy. All right. Oh, and I'm taking the derivative as I go, so just bear with me here. I think you can validate each one of these. We've got n's and natural logs of n and so on like that. Remember, the derivative of log of x, natural log of x, is 1 over x. Okay, but there are 2 other tricks that I had to derive to get this to work easily. And let me show these to you before we go. I'll just put them in here as a side note. This will make the next step easier. Now, I'm not going to follow this quite on the fly, but if you look at it on paper later. The derivative of the log of x by dx. Let's see here. Okay. This is it. I think this is the only thing I had to work out. The derivative of the log, natural log, of a minus b with respect to b. I had to do a few steps here. That turns out to be, well, let's see, it's 1 over a minus b, all times the derivative of a minus b with respect to b. And that all turns out to be, let's see, dA minus b over dB. You get negative dB by dB, and you wind up with 1 over b minus a. Okay, that turns out to be key, where we have the natural log of that n minus n up that comes in later. We're going to have one thing minus another with respect to, anyway, d log a minus b by dB is 1 over b minus a. I'm going to use that. Okay. Phew. First term, we had n log n. Derivative with respect to n up is 0. See, we're off to an easy start here. The next term, negative n up log n up, with respect to n up. Okay. So negative, we've got n up times the, let's see, first times the root of the second, plus second times the root of the first. Derivative of the second term is 1 over n up. Oh, that's convenient. This term becomes 1. But we have a derivative of the product. So now, derivative of the second, let's see, minus derivative of the second times the first. Or, I think I did it the other way around. Plus, all right, the derivative of the first term, yeah, so negative, that's 1 times natural log of n up. Okay. This was all, let's see, that was the first term. This all came from the second term. The third term, now we have negative n log of n minus n up. Take the derivative with respect to n up. So we get negative n times 1 over n up minus n. And the second part of that product is just going to be 0, because the derivative of n with respect to n up is 0. Okay. And now our last term is positive n up log of n minus n up. Take the derivative with respect to n up. N up times 1 over n up minus n. Okay. Plus, well, the derivative of n up with respect to n up is 1 times natural log of n minus n up. Close braces. Okay, that's a gosh awful mess. But each one of those was straightforward enough in its own, but it's just a whole lot of them together. Now let's combine the terms here, collect the terms. Okay, so we're going to have a first one here, that's a minus 1. Minus log of n up, minus n over n up minus n, plus n up over n up minus n, plus log of n minus n up. Close brace. Okay, now here, we take a careful look. We've got n up minus n in the denominator of both of these. We can add these two together. The numerator then, when we add these two together, becomes n up minus n. N up minus n over n up minus n is 1. That's nice. Oh, look at this. We have a minus 1 over here. So this cancels out that. Things simplify after that first terrifying few moments. Okay, k times, braces, natural log of n minus n up. And what's left over? Minus minus log of n up. Let's combine these. We've got the difference of two natural logs. Which means we can take the ratio of the arguments here. Now see, that's not so bad. That's manageable. But you know what? At this point, maybe we ought to get more sophisticated. Let's say we've got an actual paramagnet, which this is called, and a collection of, a mole of these little magnetic dipoles. Which one of you wants to volunteer to count how many of them are sticking up? There's liable to be a lot. And kind of a difficult to count number of them. But what do we really have more access to? We've got access to, or we're interested in total energy, or magnetization, things like that. So can't we use things like U or M, energy, magnetization, more natural things to measure to get rid of that number pointing up here, which in practice we don't really go down with a magnifying glass and look at. Well, one is actually kind of straightforward, honestly. If we take a look, we remember that, let's see, I'm going to carve out a little section here. This is within there. All right, over here. Since U equals mu b times 2n up, okay? There's a clever little thing we can do. Now, what you could do, the most straightforward thing to do, would be simply to solve for n up here in terms of u, and then plug that into here and here, right? It's straightforward. I'm going to cut a few steps, because there would be a few lines of resolving those terms and adding and subtracting things. And I want to put it into a fairly elegant form. So I'm going to, since I already know the answer, I'm going to do it in a somewhat more elegant way that's not as obvious at first. But you could get to it by just solving for n up and plugging in there. So here's what I'm going to do instead. That gets us a somewhat neater result more quickly. Let's see. Divide by UV. So that's n minus 2 and up. Now, if I were to take, because I already know the answer, if I were to take n minus u over mb and n plus u over mb, n minus u over mu b and n plus u over mu b, I get a sort of antisymmetrical result. Show you what I mean. So let's take this over, let's do one little derivation over here. Okay, n minus u over mu b. So n minus this, that gets us, let's see, n minus that, and then we have a plus that there, so 2, positive 2, n up. And if I were to take this equation here again, that's the same code, splitting it this way and splitting it that way. And I solve it for n plus u over ub. Okay, so I have n plus n minus 2, so I have 2n minus 2n up, so I have 2 times n minus n up. And look here. I've got n minus n up over n, over n up. 2 and up is that. 2 times n minus n up is this. So the argument here is simply, let's see. If I take the ratio of this over this, all right, that is, well, let's see, first of all, the 2's cancel out. And then if I equate those to these left-hand sides, it's the ratio of, now let's see, that over that. There. Okay. So the ratio of that divided by that is, of course, the ratio of that over that. And those 2's cancel out, which gets us exactly what was in the natural log's argument right here. So I think I didn't state that more clearly. Anyway, I can now take this, let's see, that is what's in the natural log, and I can replace it with this in terms of things we know about the system. Let's see. Now, isn't that sort of a pleasing result here? Think of this aesthetically. K times the natural log of n plus u over mu b divided by n minus u over mu b. It's anti-symmetrical. The sign flips from top to bottom. Now let's take this. This is our derivative of entropy with respect to the number up. And we want to put it back into the formula, the equation for temperature. There. Okay, so that long walk we just took was all to get let's see, we've got a K output, so negative K over 2UB times the natural log of there. And tilt this down just slightly. Phew. Now, why would I actually have wanted to put it in these terms? Well, remember, we've got, in principle, we've got access to, or we're interested in, total number, total energy, magnetic moment, magnetic field, those things there. And what I'm going to show you, we'll do this in the next lesson, is that when you have this here, we have this natural log, so we're going to wind up taking and to exponentiate both sides later on. And we're going to wind up with an exponential here with that minus sign over an exponential here with that positive sign. And we're going to get a hyperbolic trig function. which is going to give us some weird properties for the system. But that's as far as I'll take it today. We've got the temperature as a function of energy. And then when we solve for energy as a function of temperature, we'll find these interesting. Well, in fact, we'll already find something interesting here. Is there a question you got on the derivation then?
Where did you pull your 2UV in from? Above it. Okay, I see that. But then you flipped your LN, because on the other ones you have your K of LN.
Which line are you? Oh,
Right here on your final, right there.
Mhm.
You have your negative on top, N minus.
did I do that wrong? I did that wrong. Hold on. Oh, wait.
Because
I did do it wrong. You're right. Thank you. Okay, what I did, let's see. What I should have done here is, if you have log of A over B, it's negative log of B over A, right? There. I should have gotten rid of that negative sign when I did that. You're exactly right. Yes, that's it. So and I forgot, I had it correct on my paper here. What I had done was, I had it N plus over N minus originally, but by inverting this in the natural logarithm, I can get rid of the overall negative sign out front, which is just, there's no point keeping it around. Any other questions? All right, we'll end that here. And in the next lesson, we'll derive the large-scale properties of the paramagnet, and we'll wind up discovering the fun and joy of negative absolute temperature.